in red.
No.
Okay, so last part. Now our goal is to do the other way around. We start from a conventional, rather, let's say, standard open system dynamics. And we try to see how a collisional models come out. So the idea is, let's say, I mean, once again to show, but let's say the other way around, that collisional models describe, say, real dynamics. So again, this real, it's a little bit like a time-dependent concept, because what is real and what is not, it's, let's say, in becoming. But let's say that this was the original, let's say, motivation and the original, let's say, idea behind these models. I mean, these models, I don't remember exactly, but they are probably being introduced in the 60s or something like that. So let's say the possibility of building models behaving like a collisional model were far away. So the idea was to use this as a tool to describe some continuous, let's say, continuous time dynamics and so on. So it's interesting to see that you can do the other way around. You can start from a completely conventional model and get a collisional description. So, I mean, we will focus directly on an example, and we will construct the collisional description of this example. And the example that we are considering is the case of a white noise bosonic bar. So let's start by, let's say, deriving the model, and then we see what we can do. So the system, for the moment, I don't commit. So the system, it's, let's say, a single, let's say, a single part, let's say a single quantum system. Let's say you don't have, let's say, any many body dynamics, single quantum system. I don't want to commit too much in the sense that for the moment, let's say this can be both bosonic or fermionic. So let's say it can be a qubit, or can be an harmonic oscillator, or can be whatever you want. I don't want to commit for the moment. Well, instead, I commit immediately with the buff, saying that this is given by a continuous, continuous of bosonic modes. So by that, I means that, let's say, the buff is described by, let's say, creation and annihilation operators, bosonic, that satisfy the usual relationship and this is a continuous. So this is, let's say, a set of harmonic oscillator, a continuous described by frequency omega, and they are bosonic, so they satisfy this commutation relationship. Okay, so let's start by this, and let's say that the Hamiltonian describing our system take the following form. So again, the HS, I want to be for the moment, let's say, again, don't commit too much. So I simply put a dagger A, and I put omega 0. So the only, if you want, the only interesting thing is this omega 0, which tells you, let's say, the proper energy scale for the system. then the buff, the Hamiltonian for the buff is given by this. Okay, let me write, and then somebody should already complain. And then the interaction. So let's say the V, what is? The V take the form gamma over 2 pi. Yeah, again, from minus infinity to plus infinity in the omega A dagger B omega plus A B omega dagger. Okay, so these are, let's say, the rules of the game. And as I said, somebody could already raise their hands, raise the hand and complain. You want to complain? Yeah.
The negative
Exactly. That is scary, right? And not very physical. Other complaints, minor, much minor. Okay, the other complaint, but way minor. I mean, the true complaint was this. The other complaint could be here. I mean, this is very realistic. So assuming that, let's say, we have coupling constants that are omega independent is extremely realistic. And then super sophisticated people could even complain about this, saying, but this is really for super sophisticated. People could say why you don't put terms like A dagger, B dagger plus A. Let's say there are one immediate complaint, one a little bit more, less, and one really for well-educated people. But okay, let's see that all these complaints can be, let's say, cured by a single argument. And let's focus on these two. Let's say this and this.
No spectral density. No. For mass.
No, I'm assuming that it's a wide noise, so all the frequencies enter in the same way, and if you want, it's part of the I mean, probably you could. Let's see. Let's see in a second. Okay, now I say, and now the complaint should go that, let's say, again, forget about this, but let's focus on this and this. I'm saying that both, let's say, these two problems are, let's say, cured by assuming weak coupling. By weak coupling, I mean that gamma is much smaller than omega z. Why this cure all the complaints? Let's say the two main complaints. You have a proposal?
No, I don't know if I'm following.
Eh?
I don't know. If I'm
Okay.
following
Okay.
this.
Is there anybody that wants? Yeah.
You had in the last class said
My or Jamir? Mine.
Your,
Okay.
that the V interaction was much stronger than
Yeah.
the HS. So
This was something that, you know, I was emphasizing even in the first, that assuming that V is much stronger than the other look very weird, very weird, because we said in Jamir lesson, and now it's coming back again, that the interaction is very small. But actually, what I was saying last time, let me repeat, is that in a sense, the weak coupling interaction is built in the fact that you have one and C at a time. The fact that, let's say, the buff is interacting by one ancilla, and so on, it's already a weak coupling, really, because not all the modes are interacting all together. Now, somebody has an idea on why this take care of the complaint? No, okay. So the idea is that if, okay, let me help you a little bit. If this is true, only omega very, very small effectively participate in the interactive dynamics. Do you see why?
Because faster omega will, by the golden rule, not cause transitions.
Bravo. Good. Yes. Again, this is something that I always joke. The only thing that physicists can do is not even second order perturbation theory. Typically, it's even first order perturbation theory. So in first order perturbation theory, we know that in order to cause transitions, we need that the delta E between two states that are interacting must be, let's say, G divided by delta E must be close to 1. This is the resonance condition, for example. Two, let's say, single particle levels, two levels interact if the strength, let's say, the matrix element, the strength of the you understood, the strength of the matrix element is of the same order of delta E. Right? Now, let's assume that you have one state EA. So let's say that you are in absence of interaction, so V is 0. And so your states are, let's say the couple state. You have one number state for this oscillator, okay? And you have one mode of this guy. And then you do a transition to something that goes like EA prime, EB. Now, and you do this transition via an A dagger B omega, let's say. So delta E become of order EA minus, plus EB minus EA plus omega 0 plus EB minus omega 0 plus omega. Right? Yes. And this goes like omega. So the strength that you are computing is gamma divided by omega. So since gamma is very small, only omega very small can make this ratio of order 1. So the only omegas that really, let's say, play some game are the omegas very small. So they are, let's say, only the frequencies close to omega 0 effectively, let's say, what's the name? Effectively hybridize, create hybridization between the harmonic oscillator, no, not the harmonic oscillator, the system's state and the modes of the band. Good. So this, let's say, cure this, because then you say, okay, these modes are just fake. They are just there as spectators, so let me put minus infinity, who cares? They don't participate to the game. And then this cure also this. Why? Because I mean, now should be easy why this is, the white noise is becoming a reasonable, let's say, approximation. But by construction, right? Because only a small window, so let's say here is the set of all the omegas, here is omega 0, and only a very small window around is interacting. So I can say that this gamma is a sort of, let's say, average gamma bar omega for omega very close to omega 0. So it's essentially gamma bar omega 0.
Okay. Just
Please.
The first problem, said it solved because
So the first is this, because effectively the other modes are just
don't contribute.
exactly, they don't contribute.
Maybe another way to see this is you go to interaction picture. So
We will go there. Exactly. So they don't do any role. Yes.
But my issue is that now if you had a dagger, B dagger, now you would get let's say, another valid reason over that. Like, it's not
No,
possible.
no, good point, good point. The point is that when you go to the interaction pictures, these modes, let's say, in order to create a resonance, they will, this is exactly what Jamir was saying yesterday, they will, let's say, oscillate very fast, and so they average to zero. So effectively, it's a little bit more, let's say, cumbersome to see, but effectively the weak coupling is also, let's say, filtering out the other terms. So the rotating, if you want, the rotating wave approximation, which is, let's say, no, we can say differently. Yeah, I
I
think
see your point. My question was that maybe you get some other resonances at other points of the spectrum rather than omega equal to zero. That was, let's say, the complaint.
right,
Let's read
but
them.
I was saying, cioè, in order to get the resonances, you need a very fast oscillating term, because let's say the different, when you go to interaction picture, this guy get a contribution like this, right? And this omega, in order to have a resonance, this omega must be very large, and so oscillate very fast, and so effectively doesn't contribute. Effectively at the end doesn't contribute, but we are gonna don't consider this term at all. Okay. Okay, now our goal, as I said, is to extract from this a collisional model. So we have to do a little bit of the gymnastic in order to arrive there. But I promise that it will be rewarding. Okay, so the first step in order to arrive there is to introduce another set of modes that are not the normal modes for the buffer. So these are the normal modes of the buffer, but it is to introduce other modes that people call with good reason the so-called time modes, which is, let's say, a nice name to say simply the Fourier transform. So effectively, what we do is to define Bs equal to 1 over square root of 2 pi, the integral over omega of d omega b omega e to the minus I omega s. And okay, a little bit of gymnastic, but not so much, show that Bs prime is equal to 0, and Bs deg prime is equal to delta s minus s prime. So we just did the Fourier transform, and we have the same commutation rule, and so on. But now we have this point. Now, the next step that you were already advocating is to go to the interaction picture. Go to the interaction picture. So, and we go to the interaction picture with respect to, let's say, H0, that is HS plus HD. Okay, and so we know very well that A goes to AI equal to A e to the minus I omega 0 t, and B goes to BI equal to B. Well, I mean, yeah, there is an omega everywhere, I didn't put. But become clear here, e to the minus I omega 0 plus omega t. And so we know that, let's say, the new equation of motion become sigma dot equal to minus I the I sigma, where this is in the interaction picture. Notice that here absolutely everything is unitary because I'm evolving everything, I'm not tracing out anything. So this is just a standard Schrödinger equation. But now the magic starts to appear here when we compute this guy. So let's compute VI. So VI, of course, is the root of gamma over 2 pi integral minus infinity to plus infinity d omega a I dagger b omega I plus emission conjugate. Okay. And okay, doing a little bit of gymnastic, we get square root of gamma a dagger times 1 over 2 pi integral over minus infinity plus infinity e to the minus I omega t d omega plus emission conjugate. Where well, here I simply replace these two guys here, right? And this square root of gamma a dagger d s equal to plus emission conjugate. So this is the magic, because we see that we have this equation, and VI is now a VI of t that is simply square root of gamma a dagger b. And now plus emission conjugate. And now people should start to see very happy, to be very happy. Why? Nobody's happy. Good. No, is there, come on, is there anybody happy seeing this? No, not at all.
Means the setup we want for the
Exactly. If you want, the collisional description is exactly emerging at this point. We have that in the interaction picture, these modes at each time step, just one of them is playing a role. This is becoming exactly similar to what we were looking for, to what we were describing in the collisional description. Do you agree? And this is really the crucial result. I mean, all the rest become then massaging, but this is the crucial result, because the time, what is really crucial is that the time mode do not interact with each other. There are no, let's say, higher order terms involving more than one b at a time. There is just one. You don't have b square, you don't have b dagger square, things like that. Like the ancilla, right? And in each time step, there is one mode that is emerging and control the dynamics of the system for that infinitesimally, for that infinite, yeah.
Yeah, I have trouble understanding the system, because so the Hamiltonian from the back is not bounded from the low, right?
Yeah.
So you say, okay, I kind of don't care, because at the end, de facto, using recoupling only like couples from the perspective of the system.
Yeah.
A small window around omega 0. But from the back, if you have a bunch of bosons that are not bounded from below, all the bosons would like to be in the ground state. And as they are not bounded from below, like they want to be with a very high, very low negative frequencies. So it's like kind of incompatible, those.
No, wait. Let's see. I believe that, let's say, I agree that the harmonic oscillator, the harmonic oscillators with an unphysical frequency are unphysical. But the good point is that they are there just to, just as a spectator, right?
Yeah, but so your back only your back should be in the ground state.
Right, but the ground state is the ground state for each mode. So you have unphysical mode that's staying in an unphysical state, and okay. But then the physical state, the state that you care, that are the states that enter in the dynamics, are not bound, are bounded, and they interact. If you want, here is you have a collection of harmonic oscillators. Some that is completely unphysical, you put there just for fun.
But those are the ones that dominate the ground state.
No, because the ground state is a product, is a tensor state, is a product state, right, in which you put the minimal state. Now, you have, let's say, part of your system that is completely unphysical, but the part that enter in the dynamics is physical, and it has its own ground state that is a genuine ground state for an harmonic oscillator. I mean, it's like to say that, let's say, if you want the vacuum for the B, right, is given by, let's say, tensor, right, of, let's say, amphis, tensor amphis, a continuous of those, and then you have a set of tensors of phis, physical harmonic oscillators, and they participate in the dynamics. The rest,
Okay.
it's a joke. You got it, yeah. Others? Please.
So we usually do the collision analysis, the interaction picture. But at the end, should we go back to the Schrödinger picture? Look at the dynamics.
No, it's just an alternative description of the dynamics. I mean, I know that is a very bad answer, but in principle, why you didn't raise this question yesterday during the lecture on the with Janine?
Because at the end, the limit line is in the Schrödinger picture.
No,
Yeah, because otherwise you don't have the unitary part. Interaction.
we're saying interaction.
No, because if you don't have the unitary part. When you
The interaction picture, you have the
Oh.
unitary.
No,
Oh, okay, I mean.
but again, wait, this is, I think, it's my freedom to decide to go in which picture I
No,
am.
yeah,
But I can describe the dynamics in, and you don't have, it's not legal in principle,
No,
your
no,
question.
no.
I am joking, come on. But you understand what I mean. I mean, it's a matter of your preference. Okay, here there is a point. Here there is a point, and to be honest, I don't have a convincing answer. The point is that you might say, well, but you recover a collisional model only in the interaction picture. This sounds a little bit artificial in the sense that in order to get the collisional, you have to choose. Be honest, I don't have a good answer. I can just say that take it as a black magic that there is a description in which you get the collision. I don't know what else to say. But again, probably there is nothing, let's say, again, illegal about that. It's just that you get a nice description, nice, again, depending on your taste. To me, looks nice because I like collisional models. But let's say the collisional models emerges only in the interaction picture. If you don't want to do that, good luck. You do the picture that you prefer, and you don't get the collisional. But yeah, the choice of the description is completely arbitrary, I would say. Others? Okay. Yeah. Okay. So, but was wrong what you said, because this is really the point. Right? The collisional model emerged. We still have to suffer a bit in order to get the collisional model. So far, we just saw that a sort of let's say let's say continuous time version of the collisional model is already emerging by doing this trick of introducing these time modes and then following the algebra. the point is that it's true, cioè the collisional model emerge only in the interaction picture, at least in this form. I don't know if you can recover by some other tricks going to the others, please.
Okay. Can you explain again how collisional model?
Well, if you
So
want,
collisional
because if you
model-
want, okay, good, yeah, let's, okay, this was in any case intended, so let's do it. Okay, so, okay, you agree that you have this equation of motion for the full system? Yes, well, here there is VI. Now, you take your definition of VI, in which you throw away the old operators and you put the new one, where the new one are the interaction picture. This is the standard recipe. You do the algebra, you end up to this equation. Now, this equation is telling you that a time equal to t, the dynamics is controlled by not all the modes. Here you have all the modes. And here, if you want, you have all the modes, because S is a continuous index. But at that precise instant t, the dynamic is controlled by only one of them, the mode at time t. This, again, not yet fully, but start to enter in the mindset in which you are getting a set of ancillas, a set of modes. Each of them interact for a very tiny amount of time, an infinitesimal amount of time nearby t, and then go. You agree? Okay. Good. Again, this is not yet the end of the story, fortunately, also because we have more than half an hour, but let's see what we can do more. Okay, now we see, let's say, in a sense, the price to pay for having decided to go to the interaction picture, in the sense that once we do that, what did I write? Yes, we end up with the, if you want the time evolution operator, now it's time dependent because P is becoming time dependent. So we have the time evolution operator UT that is, let's say, the time ordering product of e to the minus I T0 T V I S in the S. Okay, I simply, let's say, exponentiate and take the time ordering product. And now our idea is to fully recover the collisional model. So what we have to do is a coarse graining, because I mean, we need to introduce discreteness at a certain moment, otherwise the collisional model will never emerge. So what we do is to, let's say, we have our T and we do a meshing. Each of them is of delta T, and so we start to have Tn equal to N delta T, and T0 is equal to 0. And now my dynamics, U, let's say T, become U T divided by delta T, U2, U1, where each UN is given by the time ordering product of e to the minus I integral from Tn minus 1 Tn ds vs. Okay, and now, if you want, as usual, what I can do is to, let's try here. If you want, I mean, in languages, what I'm doing is a trotterization, right? I'm trotterizing the full time evolution operator in small steps. And now what I can do is, again, a second order expansion of this beast. And so I get that my UN is equal to the identity minus I Vn delta t minus I Vn square delta t square, where my Vn is now 1 over delta t square, 1 over delta t integral between, I mean, this integral, if you want, Tn minus 1, Tn ds in Vs, and notice that we get gamma over delta t a dagger Bn, where Bn where Bn is equal to 1 over square root of delta t integral between t minus 1 t n of dt b. And finally, again, algebra, you can show that Bn prime commutator is equal to 0, and Bn prime dagger commutator is equal to delta n prime. So we finally arrived via this procedure to a real collisional model. We have a meshing of the type. At each time step, we have a well-defined unitary operator in which the Vn entering here is built in terms of the, okay, sorry, here there is the initial conjugate. We have an A dagger Bn in which the Bn is, let's say, a discrete creation and annihilation operator. Each of them satisfy exactly the algebra that we were looking for the collisional model. So now we really have a collisional model. Notice that we are getting another old friend of our, the fact that we have a diverging coupling constant emerging. So this is really a collisional description. So summarizing, and then we go to the last part, the very last piece will be fast, so we are gonna finish earlier. Summarizing, what we have seen is that a fairly, let's say, honest open system dynamics in the weak coupling approximation and described in the interaction picture give rise naturally to a set of modes that in the interaction picture interact with the system one at a time in a continuous way. This could be the endpoint. If you really want to go close, I mean, finally to the conditional description, you have to do a coarse graining because the conditional description requires a coarse graining. You do the coarse graining, you bring the coarse graining at the level of unitary evolution operator in each time step, and you end up with a diverging coupling constant, good point, and an algebra that is exactly the algebra of the oscillators that enters in the description. Question, and then we do the last comments. Yes, I was looking for you.
The third term there in the expansion of the UN, that was correct?
Is it wrong, you think?
Yeah.
What do you mean wrong or correct?
The UN equals unity minus one.
Sorry, no, it's wrong, of course. Yeah, thanks. It's absolutely wrong. Minus 1 over 2. Is this the complaint?
Yeah.
Absolutely. Yeah. Thanks. Absolutely. Yeah. Sorry. Other? Okay.
No.
Yeah, please. What is?
So there you're dividing by delta t,
Mhm.
and then you substitute this VI the integral, right?
Repeat, sorry.
We have the VS, which is a VI functional S, right?
Yeah, what I wrote, yeah, the VS
Then
is,
it's
if you want, the VS is this, The VS is this, because if you want, actually, okay, yeah, sorry, I should have been more precise. VS is this, is VI at the time S. Is the interaction in the interaction picture at the time S. I do the integral. The delta, you could ask why you put the delta t here. The delta t is such that the Bn has the right.
I would think that it's delta t from the integral. Hence, it's delta t in the denominator. So I don't see how you get 1 over square root of it.
Okay, let's see. Let's see.
There is a square root in the Bn definition.
Let me see. Probably I made a mistake.
I think there is a definition of Bn with 1 square.
It's 1 over square root.
Let's see. Probably I did a mistake somewhere. Okay, here I wrote. Here I wrote what I wrote in the blackboard. But yeah, I agree. Let's see, because VS is that. Ah, no, wait, but I'm reabsorbing. Here there is a delta t, right?
Okay.
And there is a square root of delta t. So here you get a delta t, 1 delta t, you get cancelled here, let's say 1 square root of delta t, and the other square root of delta t gives the square root of delta t here. Okay, yeah. And this square root of delta t is important here in order to create good commutation relation for the Bns. Okay, thanks. Okay, last comment. Where are the ancillas? Here we talk about ancillas at the level of modes, at the level of, but ancillas are also given by a state. So far we didn't talk about the state, right? Just okay. So where are the ancillas? Okay, the ancillas enter because if you want, okay, let's say what we got so far is a conditional description without saying a single word about the state of the buff. Right? We didn't say anything. Just say the buff is there. We didn't took any trace. So the state, the buff is there, and we didn't say any word about its own state. So the last, okay, yeah. So we have to, if you want, the last piece that is missing is what is the state of the buff, and here, case by case. So let's do one example, and then hopefully you will trust me about another interesting example. So the single example that we will do is suppose that, let's say, the state of the buff, let's say rho p is equal to the vacuum. And now to come to you, I mean that I'm just focusing on the modes that are physical. So this is the vacuum for the modes that enter in the dynamics. The others are there as expected. So this is the vacuum. So what is the definition of the vacuum? The definition of the vacuum is that each p omega acting on the vacuum is equal to 0, right? This is the definition of the vacuum for each omega. Now, by doing all this step, so essentially what we have to do, we have to come here. Bn is a linear combination of B. Yeah, it's a linear combination of the various Bt. The various Bt are, so, okay, it's easier if I add it. So the Bn are 1 over square root delta t integral dt dt equal to 1 over, well, okay, 1 over 2 pi delta t integral in dt integral in d omega e to the minus I omega t d omega. So if a state is completely annihilated by all of them, will be also completely annihilated by all of them. So we can say that putting this, it's equivalent to putting, let's say, the vacuum. Let's say that we get some rho n for each mode. This is 0, 0, n. So if our field, if our bath was in its vacuum, this translates in the corresponding vacuum for all the modes, that are entering there. Probably there is a caveat because I'm doing an integral over infinity, so probably I need to regularize in some way. I don't know. Yeah, I know where you want to go, and yeah, probably there is a caveat, but there are ways probably to cure it. Let's say that it's reasonable that, yeah, forget it. Anyway, so this is what I get. So all the ancillas are coming in the vacuum, and I'm getting exactly what I was expecting. If you want this model, if the system, okay, another important point. Suppose now that the system is a qubit, is a two-level system. Now, since the interaction preserves the number of excitations, the only states of the harmonic oscillator that I can excite are the 0 and the 1. So it's actually, because I don't have others, I can go up at most by 1. So actually each incoming ancilla is behaving like a qubit because it has only the 0 and the 1. So it's behaving like a qubit. So I recover in the situation in which I had my own qubit collisional model, right? All qubit collisional model in each ancilla entering in the vacuum. And that was describing, you remember, the radiation of a two-level atom in a bath. That is exactly this description. Now, the state that was time-dependent, you can do similar strategies and show that correspond to the bath being in a coherent state. So that crazy ancilla time-dependent was actually in correspondence with just the bath in the coherent state. Okay, I think we can stop here. We are a little bit in advance, but more or less is that. Now, depending on how it works, if at a certain moment there is some free time, I could do an extra lecture about the micromaser. If people want to hear, if there is no time, next time. Okay, for questions, yeah, we can chat at the various coffee time.
Pero so perché non si ci sento tutto. Io non sei fare le competizioni, sai che devi
Okay, that is, I agree. That's
not sure, 3 hours.
if I say that live system is,
Remember,
let's say.
no, wait, what did you say? Three, I think so.
No, but
There, Portava a serva al proprio le cose da.
Thermal bath?
okay, I know.
Thermal bath.
I think it's not correct to see ground state. I stay in the ground state for the the other are not even there, cioè they don't participate to the analysis, the other.
Okay, but that is like
Are we going to lunch?
Yes, yeah. Lunch with Dario.
Yeah, okay.
Technically,
Yeah. What is now? No, yeah, I'm a dinosaur.
I read some.
Yeah.
To be honest, I don't even know
What the direct.
why you need that, why you
For somebody to lunch, but people want to go to the mall.
Why is
Oh, yeah, that's what I do. That is the reason. That's
Like, sir.
Okay, so let's see. So you.
Yeah,
Okay.
well,
Now you assume
we
that
don't
you have.
factorize into the
But the most, right, and then I have like, because like.
No, you assume that you are.
It's the same on
Yeah, exactly, yeah, exactly.
side.
You want
It's like,
infinite of infinite,
Well,
much I do not say, right?
how do I exactly what of this, right?
Yeah, but this is like just like some metrics.
But what I call the back again,
Yeah.
is not the back.
Makes sense.
You are working in a situation in which you have whatever occupation that you are on the walls of the garage, that is, doesn't pay. So that works in the state,
Yeah.
let's say, zero variable
This is weird, right?
in. No, but actually.
So,
no,
but
wait,
what-
wait, wait, no.
Okay, but you're doing it cheese for vacuum for the dogs and what's
Like this.
I mean.
This is a typical,
No, but that is.
Yeah, but like what you were showing, I mean. Yes.
algebra is.
Like, what define vacuum is, I mean, also like what I was thinking, no, it's like where, I was just. Where the word is.
I didn't.
Right, like where.
Who tried to invade any other?
Just think of all the tensors.
Yes, and,
Okay.
okay, that was now, I was thinking, it's not like, it's not like the.